If I have two copper wires with the same diameter, but one is longer than the other, you can expect the longer wire to have a higher resistance. That's because an electron needs to make its way between more positive ions before it reaches the other end. So here, we've established that resistance is proportional to the length of wire. In a different situation, we have two copper wires with the same length, but this wire has a larger diameter so that it has a larger cross-sectional area. In this wire, the electron has more options to choose the path of least resistance. This shows that the larger the cross-sectional area a wire has, the lower the resistance there is, so resistance is inversely proportional to area. But what if we have two wires with the same dimensions, but this is copper and this is steel? Copper is a much better conductor of electricity compared to steel. We need a way to specify how much electrical resistance a certain material has. We call this measurement the resistivity. We give resistivity the symbol ρ. Since resistivity is a constant for a particular material, and we know that resistance is proportional to length but inversely proportional to area, we can now write an expression for the resistance of a material. Resistance is equal to resistivity times the length divided by the area. Let's use dimensional analysis to work out the units for resistivity. I'll rewrite this first to get resistivity as the subject. The units of resistance is ohms, units of cross-sectional area is meters squared, and length is just meters. So the units of resistivity is ohm meters. For example, copper's resistivity is 1.7 times 10 to the minus 8 ohm meters. But steel's resistivity is 6.9 times 10 to the minus 7 ohm meters. So if I compare a copper wire to a steel wire with the same dimensions, the steel wire will have a much higher resistance. Some of you might be wondering by now, what is the difference between resistance and resistivity? Resistance tells us how much an object opposes the flow of electrons. It is dependent on the object's size and the substance that it is made of. So we say that resistance is a geometric property, but resistivity is an intrinsic property of a particular substance. It does not change with the material's geometry. So if I double the length of this wire, the resistance also doubles. But if I double the cross-sectional area, the resistance is going to half. But in both of these cases, the resistivity remains unchanged. Thanks for watching till the end of this video. If you found it useful, be sure to subscribe.
Electrical conductivity. Electrical conductivity is a measure of how well a material accommodates the movement of an electric charge. Its SI derived unit is the Siemens per meter. The materials which allow electric current to pass through them are good conductors of electricity. On the other hand, materials which do not allow electric current to pass through them easily are poor conductors of electricity. You know that metals such as copper and aluminium conduct electricity, whereas materials such as rubber, plastic, and wood do not conduct electricity. Good conductors have higher electrical conductivity than insulators.
Electrical charges generate a field around them. These fields of force repel and attract other electrically charged particles. Like charges repel, and opposite charges attract. When enough of these charged particles are separated, a potential difference is created. Electromotive force is a potential difference measured in volts. The symbols commonly used for electromotive force are E or V. The potential difference in charges is what forces electric current to flow. There are 7 fundamental forms of electricity generation. All of these forms of electricity generation create an electromotive force, or EMF. One of the most commonly used forms of electricity generation is the electrochemical reaction, or better known as a battery. The potential difference across two open terminals is known as the unloaded voltage. The electrical potential difference forces current flow when a circuit is attached to the source of EMF. There is typically some amount of resistance in all electrical components and devices. When current flows, the voltage across the terminals of the source of EMF is no longer the unloaded voltage value. There will be a voltage drop inside the device due to the internal resistance of the EMF source. When the circuit was not connected, the battery had an unloaded voltage rating of 1.5 volts. Once the circuit was connected and current started to flow, there was a voltage drop across the internal resistance of the device, and the applied circuit voltage was reduced to 1.3 volts. The DC power supply is a commonly used device in the lab. This device has the ability to create different amounts of electromotive force. As the voltage is increased, the potential difference between the terminals is increased. Note that the unloaded voltage of the power supply is set to 5 volts. A DC power supply will experience a loss of potential difference due to the internal resistance of the supply. When the circuit is connected and current starts to flow, the internal resistance of the power supply reduces the applied circuit voltage to 4.7 volts. Electromotive force is the potential difference that forces current to flow in a circuit. We have looked at a couple of different sources of EMF and at some practical applications.
Okay, in today's video, we are going to go over an introduction to electric power. We're going to be talking about DC electric power in this video, and this is the equation. This is the definition, the most common definition I think you'll see for power. The most general definition, oftentimes you'll see this when we talk about mechanical power. It just says that the power is the rate at which work is done. It's how fast you do your work. For electric power, we like to give a little bit more specific definition. It's the rate at which electrical energy is transferred to a circuit or to an element in a circuit. Because what happens is, in a circuit, for electric power, you have electrons, and the electrons get their energy from a voltage source, typically a battery. We measure that energy in volts, which is joules per coulomb, which is electric potential energy. So it's kind of the amount of energy. A volt is the amount of energy that's per coulomb of charge. Now, when the electrons move through that circuit, then they collide with the atoms in the elements that are in the circuit, such as the heating element, or like if you have a toaster or a hair dryer, the electrons are actually moving and colliding with the components in the circuit because they have a higher resistance, and then they transfer some of their energy, or they transfer all of their energy to those components, and then that energy is typically converted into heat or light or motion. And that's what electric power is how fast that transfer of energy occurs. All right, now for some real basics about electric power, whether talking about mechanical, electric power has the symbol P. It has the units, the watt, which has the abbreviation capital W. And for example, we would say the power is equal to 1800 watts. We write P is equal to 1800 W. We don't say P is equal to 1800 W, we just say power is equal to 1800 watts. 1 watt is equal to 1 joule of electric potential energy being converted or being used every second. So we say that a watt is kind of the abbreviation for a joule per second. So for example, if you have a hair dryer, here's a hair dryer, it's an 1875 watt hair dryer. It means that it is converting 1875 joules of energy per second into heat in this case. Now you can also see this very common in a light bulb. It's a 2-watt light bulb, an LED light bulb. It's using 2 joules, or converting 2 joules of electric potential energy per second. This light bulb gives off as much light as a traditional, maybe incandescent 60-watt light bulb. And the last thing we have here is a food steamer. When you use a 120-volt source, this food steamer will produce 900 watts of power to heat and steam your food, 900 joules of energy, electric energy, is being converted every second. Now we're going to go through the equations, how we calculate electric power. We're going to start off again. This is kind of the most general equation for power. You see this most commonly with mechanical power. The power is equal to the work done divided by the time. It's the rate. It's how fast you do work. But for electric power, we can say that the work is equal to the charge, the amount of charge, and the potential difference through which that charge is moved. Because when we move a charge through a potential difference, we do work. We can substitute that into our equation for work. That means that the power is now equal to the charge times the voltage divided by the time. We can get out our equation for the current, because the current is the coulombs, the amount of charge per second that passes a given point in the circuit. Solve that for Q. Q is now equal to E. I times T, and substitute that into our equation. Now we have power is equal to the current times the time times the voltage divided by the time. Those two times are the same, they cancel, and this is kind of the most common equation you'll see for electric power. It says that the power is equal to the current times the voltage. Now there are two other equations you should be aware of for electric power, and we get those equations by substituting in or using Ohm's law. V equals I times R. You can see that have the power is equal to the current times the voltage, and the voltage is equal to the current times the resistance. We can substitute IR in for V, and one of the other equations is the power is equal to the current squared times the resistance. Okay, and the third equation we can get from now taking Ohm's law, solving it for I is equal to V divided by R, substituting that into here for I, and the power is equal to the voltage squared divided by the resistance. So these are the three equations that you use to calculate electric power. There's kind of three things here: the current, the voltage, and the resistance. If you're given the I and the V, you use that equation to calculate power. If you're given the current and the resistance, you use this equation to calculate the power. If you're given two things like the voltage and the resistance, they use this to calculate the power. Now, let's do a couple of quick examples. Here's a DC traction motor. You can see here we know the power, so we know the power. We have the voltage, and we want to calculate the current. This is the equation we're going to use. Solve that equation for the current is the power divided by the voltage. Substitute the values in, 5,000 watts, because this is 5,000 kilowatts, divided by the voltage of 72 volts, and you get that when you use that DC traction motor with a 72 volt source, it is going to pull or draw 96 amps of current. That is a lot of current. Okay, last example here. Back to light bulbs. Okay, we want to calculate the resistance of a 72 watt light bulb that draws 0.8 amps of current. We want to calculate the resistance. We're going to use this equation or this equation. We know the power, we know the current, so therefore we're going to use this equation. That is P is equal to the current squared times R. We want to know the resistance. Solve that for the resistance, the power divided by the current squared. Plug our values in, 72 watts, 0.8 amps squared, which is 0.64, and we get that the resistance of that light bulb is 113 ohms. Okay, so there you go. We went over definition, kind of explanation of power. I went over the specifics like the units and the abbreviations. I showed you how to get the three equations for calculating electric power, and then we did a couple of quick examples. So I hope you found that video helpful. If you did, please do all of the following four things now. Subscribe to my channel, get all my excellent physics, chemistry, and math videos. Give me a thumbs up, leave me a nice positive comment in the comment section below, and don't forget, please don't forget that sharing is caring. Share this video with your friends. Show them how much you care. Thank you very much for watching. We'll see you in the next video.